computer. Okay, so this is exactly 10 a.m. I'm going to start recording. I'm going to put this on the video. I will upload yesterday's video as well before I even leave my office this time, so that I will make sure I do that. It'll be uploaded to that same channel that you have the organic chemistry on. And you'll notice that I will have if you missed this one or you want additional information, you can actually go back to there and look at chapter 3. Again, I only did highlights of chapter 3 yesterday. You need to go back and watch both videos for chapter 3 to get all of the information. Okay, so what I'm going to do now is I'm going to go ahead and share my screen with my iPad here. Let's see what happens. Yes, trust it. It's trusted. There we go. All right, iPad. All right, there we go. Can everybody see my slides from yesterday? Give me the chat or unmute, either one. Okay. Okay, yes. All right, good. So what we were talking about yesterday is bicycloalkanes. And so when we think of bicycloalkanes, we have to remember 3 things. Number 1, the name bicyclo. So that's going to be at the beginning of the word. Number 2, inside the brackets, we have the number of carbons of each bridge. Okay, so that means we have a bridgehead carbon and a bridgehead carbon. And we need to number the carbons in between those bridgeheads, starting with the biggest chain, 3, in the case of the one we see here, and then 2, which would be the carbons 6 and 7, and the 1, which is carbon 8. And again, when we number these things, the third most important thing is we start from a bridgehead and go around the largest ring, the largest bridge, to this next bridgehead. So in this case here, we're looking at going from 1 is our bridgehead. 2, 3, and 4 are our 3 carbons in our bridge. 5 is our bridgehead. Our next largest bridge is the 6 and 7. That's 2 carbons. And then our third bridge is the carbon number 8. Now in this case here, our substituent has to be on that carbon number 8. It doesn't matter that that substituent is on the lowest number, because we must label the bridge is as our longest bridge first, our second longest bridge second, and our third longest bridge third. What if you have 2 bridges that have 3 different carbons in them, and then one side has a substituent and one side doesn't? Then you number from the one with the substituent first. If they're equal, number the substituents first. Oh, there's somebody actually has set up a group me. That's a great idea. I do not actually subscribe to it. I want you guys to have the perfect, perfect anonymity there. Don't be mean, please. But there's a group me in the chat there. So if you have it there, you should go look for that. All right. So now notice there's a couple different ways we can draw this. We can draw this in this really elongated fashion, or we can draw it in this fashion, or there's even a 3-dimensional version for this right here. And so the 3-dimensional version would be something like, we're going to do there's not actually, let's go ahead and erase that one. There is 3 carbons in this one, 1 and then 1 here. So notice we have 1, 2, 3 on this side, 1, 2 on this side, and 1 on this side. So this is another representation of the exact same compound, okay? So it's just another way of looking at it. Now, when you're drawing bicyclo compounds, the best way to do it is to start with your bridgeheads, because you're going to say, okay, I know I have to have at least 2 bridgeheads. So I'm going to put 1 bridgehead here and 1 bridgehead here. Okay, then you build your first bridge. And in this case, we have 3. See, because it's 3, 2, 1. So we have 3. So we're going to go 1 carbon, 2 carbons, 3 carbons, back to the bridgehead. And then the second thing is 2. Okay, so we're going to go 1 carbon, 2 carbons back to the bridgehead. And our last one is 1. So we're going to do 1 carbon back to the bridgehead. Okay, so if you do it this way, it makes it easier to draw them, and you won't mix up where the different bridges are. You'll be able to do it very well. And then, of course, we have our substituent is going to be here because we had to start numbering at 1, 2, 3, 4, 5 around the biggest ring, 6, 7 around the second biggest ring, and 8 around our third ring. So we know that our substituent is on the correct place. We know we numbered it correctly. So now let's look at this one when we have it fused. When we have it fused, we have to think about it slightly differently. So the first thing we want to do is we want to identify our bridgehead carbons. So our bridgehead carbons are going to be 1 and 2 right here. That's not their numbers. They're just, we have 2 bridgehead carbons. Okay, but now we need to identify our rings. So we have 1, 2, 3, 4 on this side. We have 1, 2, and 3 on this side, but where's our last one? Our last one is a 0 carbon, which means it's fused. So we have a 4, a 3, and a 0. So in our brackets, we're going to do, our bracket is going to be 4.3.0, okay? And so then we're going to start out with bicyclo, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons in there. So that's non-ane, non for dime, non-ane. So we have 1 bridge with 4 carbons, 1 bridge with 3 carbons, 1 bridge with 0 carbons, and we have the substituent. Now again, our substituent is on the number 8 carbon because we had to number through the largest one first, the second largest one second, and our third largest one third. Therefore, our substituent is still on the methyl, still a methyl. So it's going to be 8 methyl bicyclo. Again, no capital here, bicyclo, and it runs together. Bracket 4.3.4.0 bracket non-ane. Okay, questions on that? All right, so let's do another one here. And let's do this one right here. So this one's going to be a little interesting because we're going to start with our bridgeheads first. So our bridgehead is here and here. Okay, now we have a choice in our bridgeheads because there's an attachment at one of our bridgeheads here. So we put the substituent at the lowest number bridgehead possible. Now, the other thing we have going for us here is we have 2, 2, and 2. So does it matter which way we label them? If there are no substituents, no. If there are substituents, you want it on the lowest number possible. So in this case here, just by the way it's drawn, we're going to have, let's see, we're going to have 1, 2, 3, 4, 5, 6, 7, 8 carbons. So that's going to be bicyclooctane. And so we're going to do bicyclo 2.2.2. No, I'm sorry, bracket octane. And then we have to put our substituent here as 1 isopropyl. Notice it all strings together. So it's 1 isopropyl bicyclo bracket 2.2.2 bracket octane. Okay, now another way to draw that is to draw it in this flat configuration. Now let's talk about how to do that again. Again, what we're going to do is we're going to draw our 2 bridgehead carbons, and then we're going to do our first set, 1, 2 brackets, 2 carbons, 2 carbons. But again, we're going to keep our substituent on the lowest number possible. So this is a flat way to do it, and this is a more 3-dimensional way to do it. But they both are representing the exact same compound. Questions on that? Okay, we're up to 16. Only one person's missing. That's great. All right, so let's do one more here. And this one's fused here, but let's go ahead and look at this again. So we're going to do that exact same process right here. We're going to start with our bridgehead carbons, which are this one and this one. And then we're going to start labeling around our system. Okay, now here we actually need to label around the system one way versus the other, because if we started here and labeled this 1, 2, 3, 4, 5, 6, 7, 8, 9, our substituent would be on a higher number than if we labeled it the other way. Okay, so we don't want to do that. We want to label it the other way, but we still have to label around the first biggest ring first, right? So what we're going to do is we're going to do, this is our 1, 2, 3, 4, 5. So because this is our 4 bridge, and then this is our 3 bridge. So we're going to go 6, 7, 8, 9, and then this is our 0 bridge because there's 0 carbons and it's a fused ring. So that means we're going to have our methyl group on our 7. So we're going to again start with bicyclo bracket 4.3.0, and there's 9 carbons in our ring system, so non-name. And then we have a methyl group on our 7, so it's 7 meth for 1 carbon, and YL because it's a substituent, so YL. So it's 7 methyl bicyclo bracket 4.3.2.0 bracket non-name. Okay, so do we see how we want to do our system? We want to do that same system every single time. Find your bridgeheads. Label your biggest bridge first, your second bridge second, your third bridge third. If they're all the same, you want to put your substituent on the lowest number possible. Questions on bicyclo nomenclature? All right, so let's get on to a different functional group. Now, when we talked about functional groups in chapter 2, we said that the hydrocarbons consisted of alkanes, which have only sp3 hybridized carbons, no double bonds. Then we had alkenes, which had at least 2 carbons that had sp2 hybridization and had a pi bond. And then alkynes, which had a two sp hybridized carbons and at least 2 double bonds between 2 of the same carbons. Okay, and then we had the arenes, which are the conjugated double bond systems. Okay, the next thing up from that we get is our alcohol system, which means we have an OH group. And if it's just we're talking about that OH group, it's called the hydroxyl group. However, if the hydroxyl group is the only functional group, we have now changed the name of our compound and it's turned into an alcohol. When we change things to an alcohol, we have to change the hydrocarbon group, which is the E at the end, to an OL, okay? So that's the big thing we're gonna start doing now is we're gonna look at all the parts of the name. Remember, we have a prefix, we have an infix, we have a suffix, and we have the number of carbons in our system. So we're going to look at all 4 of those things to figure out what we have. Okay, so in this case here, the first thing we want to look for is the longest chain containing the functional group. Longest chain containing the functional group. Okay, so in this case here, when we blow this up, we have 1, 2, 3, 4, 5, 6 carbons here. If we tried to number it from here, 1, 2, 3, 4, 5, 6, it turns out to be the same. But what it means is we have the longest chain with the hydroxyl group is 6. So we have hexa. Hexa is the number of carbons we have. So we have hexa, and we're going to drop the E. So we have hexane, and we're going to add the OL, hexanol, hexanol. Okay, so when we do that hexanol thing, we now have, because the OL at the end of the sentence tells us we have a functional group, and that is the highest priority functional group. Alkanes are low priority. Alcohol is our first priority group we have, hexanol. Okay, so now we have to number this. Now, when we're numbering, we want to give the thing that changed the name the lower number. Okay, now we could label from this side right here, and the methyl group would be on a 2 position, but we actually don't want to do that because OH changed the name. And if OH changed the name, then we have to have OH be the lowest number. So that means we have to number from the other side right here. We're going to number from this side to give 1, 2, 3. Our OH is in our 3 position. Okay. And that means our methyl group is in the 5 position. It doesn't matter that it actually is higher numbers than the name the other way because the name changed. Because it's not an E at the end, all we care about is where that functional group is, where that OH group is, and we want to have it at the lowest position. So that makes it 3-hexanol because it's lowest position. So now we're going to add all of our other substituents, okay? Okay, because OH changed the name, it controls the numbering, and then we add everything else, which means our methyl group here is on the 5. So our final answer is 5-methyl-3-hexane-ol, all, hexanol. So the name is 5-methyl-3-hexanol. Okay, questions on that? Okay. So now, every time we have a functional group change the name, we're going to follow that same rule. Okay, before, when we didn't have a functional group, we wanted the lowest number possible. When we have a functional group that changes the name, we must have that as our lowest number. All right, questions on that? Okay, so it's a little different, but it's very consistent, very consistent. Now, what if you have I'm sorry, I need to take a drink here. Okay. Okay, so when we have a cyclic compound, if we only have an alcohol on our cyclic compound, that alcohol is going to be in position 1 because you only have 1 group. So it'd be just like 1-hexanol. Well, I'm sorry, 1-cyclohexanol. But if we have more than 1 group, again, the alcohol is changing the name, therefore it has to be number 1. Now, if you have a choice, you need to try to get it to be at the lowest number. So in this case here, we have C1 is where the OH is. So that's 1-hexanol, which means we don't have to actually label it as 1 because we know cyclohexanol has to have that OH at position 1. And we're going to go around the ring to get us the lowest number possible, which is 3. So in this case, it's going to be 3-methyl-cyclohexanol. Okay. Now, if we have a choice of going around the ring, we still have to get our first group at that lowest position. So notice that if we go in this direction here, we have a 2. But if we go in this direction here, this would be a 3, 3. Okay. Those 3s are bigger than 2. Therefore, we have to go counterclockwise around that ring to give that methyl group our lowest position. Okay, so when going around the ring, you want to have your next substituent at the lowest position possible. All right, so in that case here, even though we have a total of 3 substituents here, we still have to follow that lowest one. And we have 1, 2, 3, 4, and 5. Now we have 2 methyl groups here, and we have 1 methyl group here, which means we get to do not try. Don't try. We're going to have tri, T-R-I, methyl, cyclo, 1, 2, 3, 4, 5, 6, hexane. And our positions are going to be 2, 5, and 5. So we're going to have 2, 5, 5 dash trimethyl cyclohexane. Oh, is that right? No, it's not right. We have the alcohol. So we have to drop this E and put an OL at the end. So it's 5, 5, 5, 2, 5, 5 dash trimethyl cyclohexanol. So it's cyclohexanol. Again, we're doing this because the first group has to be at that lowest number possible. Okay, so there's a lot more stuff like this in our homework. So don't forget to do your homework. It's due tonight by midnight for this chapter. Is it? Yeah, because we're going to do chapter 5 homework for notes. All right, so now let's talk about common names. In the case of common names, we don't have to do a find the longest chain. What you're looking for is what the thing it's attached to is a common substituent. So in the case of a methyl group, if a common name would be methyl alcohol. If it was an ethyl group, it would be an ethyl alcohol. But remember, we have isopropyl, we have regular propyl, we have butyl, sec-butyl, isobutyl, and tert-butyl. So you would use those substituent names to be on our system. In this case here, if we redraw this, we have OH. This is isopropyl alcohol, bunny ears. And so we would say isopropyl alcohol. Okay, this is perfectly acceptable. Again, IUPAC names are better, but this is the common name for the system. Any question on common names for alcohols? So we're going to use several of these. Isopropyl alcohol is going to be used a lot. Methyl alcohol is going to be used a lot. Ethyl alcohol and T-butyl alcohol. All of those are going to be used frequently. Okay. So what if we have more than one alcohol? Okay. Well, if we have more than one alcohol, we're going to do it exactly like we do more than one methyl group. We're going to say diol or triol. Okay. And again, when we do this, there is a common name associated with it, but there's also an IUPAC name. In the case of diols, our common name is called glycol. Glycol. So if you have 2 OHs on the same chain, you can put the carbon chain plus glycol. Now, if you have 3 alcohols on it, it actually has a special name. This is glycerol. Okay, glycerol is actually a very common molecule. It's a trialcohol of propane. Okay, and it's used in actually all of the fats in our bodies tend to be triglycerides, which use the glycerin to hook a whole bunch of fatty carboxylic acids to. Anyway, we'll talk about that later. Anyway, so when we have an IUPAC name, you look for the longest carbon chain. In this case, we have 2 carbons, which means we have eth. So that's ethane. And then we have 2 alcohols right here. And so we have ethane diol. Notice the E's there. The E's there telling us how many carbons we have. The diols telling us how many alcohols we have. So in the case of this, we have 3 carbons. So we have propane triol because we have 3 OHs. Okay. Now, if we only have 2 OHs on a propane, we're going to call it propane diol, but we have to identify each of the carbons that has an OH on it. Okay, so in this case here, it's going to be carbon 1 and carbon 2, so it's 1,2 ethane diol. We have a 1 and a 2 and a 3. We have 1 on each of the carbons, so it's 1, 2, 3 dash propane triol. So each of those numbers identifies where an alcohol is. And in this case here, we only have it on the 1 carbon, nothing on the 2 carbon, and an alcohol on the 3 carbon. So that's 1, 3 dash propane diol. We only have 2 alcohols, and we have identified them as being on carbon 1 and carbon 3. Okay, questions on that? Okay, so for rings, we have to worry about 2 things. Number one of the alcohols always has to be on number 1. And then you try to number it so the second alcohol is on the lowest number possible. So for example, if this OH was over here, we would call it 1,3. but it's not. It's in the 1-2 position for this one. But we also have to worry about rings because rings are flat, and we have to decide whether one of the groups is above the ring or if both of the groups are above the ring. If both of the groups are around the ring are on the same side, which makes it a cis compound. In this case here, we see that wedge, that solid wedge saying one of the OHs is sticking up. We see that dashed wedge. One of those wedges is sticking down, which means they're on opposite sides of that ring. So if they're on opposite sides of that ring, we have to call it a trans diol. All right, so let's put all of those words together. We have a diol because we have 2 alcohols. We have it in the 1 and the 2 position, but we have them on opposite sides of the ring. And we have a cyclo compound. There are 5 carbons in our cyclo compound, so it makes it our trans dash 1, 2 dash cyclopentane, and we have 2 alcohols, so we have to say diol. Okay. Now there probably isn't a common name for that, but there are the common names that we should know are the ethylene glycol. The ethylene glycol is basically 2 alcohols on 2 carbons. Propylene glycol, which is 2 alcohols on 3 carbons, and glycerol, which is 3 alcohols on 3 carbons. Those are very common names that we'll see. In fact, if you start reading any of your products, at home that have like names of things, you'll see all 3 of these commonly found in household products. All right, questions on Diols and Triols. Okay. If you have 5 alcohols, it's going to be pentanol. If you have 20 alcohols, it's going to be icosanol. So it doesn't matter how many you have, you just have to keep adding things to it. All right, so now all alkanes are only sp3 hybridized and there are no double bonds. So what do we do when we have an alkene, something that has a double bond? Okay, the rules change slightly, meaning that the longest chain must contain both of the carbons in the double bond. Write that down. The longest chain must contain both carbons of the double bond. Okay, so that means if you had something where you had, even if you had a very long chain like this, and you had 2 carbons out here, I'm sorry, there should be a 2 there. You have to make sure both of these carbons are in your longest chain, okay? That's what I'm saying. All right, so let's take a look at the compound we have listed here, right here. So we have to have those 2 carbons in the longest chain. And in addition to that, because we have that double bond, they have to be in the longest chain and they have to be the smallest number, okay? Which means we have to label it from here. 1, come on, from this side, 1, 2, 3, okay? We could also number it from here, 1, 2, 3, because it gives us the same carbon as the lowest number. That first carbon of the double bond has the lowest number possible. We always want to have the double bond have the lowest number possible, okay? So now, so from this case here, we're going to go ahead and erase those and go ahead and go 1, 2, 3, 4, 5, 6. This could also be 6. You're going to be the same number, but it's fine. Okay, now that means we have a methyl group on a 2, we have a methyl group on a 3, and we have a methyl group on a 5. Okay, so we have trimethyl. But how many carbons do we have in our main chain? We have 6. Okay, so that means we have hexa. Okay, but whenever we have a double bond, we drop the ANE and add ENE. ENE. So it's going to be hexene, trimethyl hexene. Okay. So because we have to have both of those carbons there and they have to be in the longest chain, our number is going to end up being 2 hexene because that 2 has to be the lowest number. So we have 2 hexene. That just tells us the main chain. We haven't even named the substituents yet, okay? So when we name the substituents, we're gonna go with a 2, a 3, and a 5. So we have 2, 3, 5 dash trimethyl dash 2-hexene. Okay. If the double bond is on the end of the chain, you don't have to include the number 1. But if it's anywhere else in that chain, you must include it. Okay. So it's always better to include it, even if it's a 1, even if you're not sure. Okay. And notice we have the substituent dash 2 is telling us where the alkene is. So it's telling us where the alkene is. And just that would be the same if we had an alcohol in that 2 carbon. We would have that 2 there to say it's hex unknown, because that 2 is telling us where the OH is. So it's the same rule. We're just using it for our hexene instead of our substituent. Questions on that? Okay. Now, what happens when you have more than one functional group? Okay. When you have more than one functional group, things get a little different, but you have to include the idea that you have a double bond, so the ene must be there. But you also must have the OH there if we have an OH on there. So we have to have the all. So we're going to see things that'll have a name that's called an ene all. Okay. Okay. So let's double check that we have our numbering right. We have our carbon here at the end. Both of these carbons must be included in our longest chain. Even though the chain would be longer if we numbered this way, not both carbons are in both of the double bonded carbons are in the longest chain. So we can't say it's octane. We have to say it's heptene. Okay. We see how this would be a longer chain if we went in this direction here. 1, 2, 3, 4, 5, 6, 7, 8. But we can't do it because both of the carbons in the double bond aren't there. So that means we have to go 1 carbon less and go to with heptene, and we have a substituent on the number 2 position. Okay, because this has to be 1, this has to be 2, etc. So the most correct name would be 2-ethyl-1-heptene. Although if you leave the 1 out, it would be understood that the first carbon would be the number 1 position, just like in an alcohol, that the number 1 position is understood to be the alcohol. So that being said, we can actually have more than one thing on here. So in this case here, we have 1, 2, 3 carbons, okay? Now, all 3 of those carbons have to be part of the main chain because they are a double bond and they have an OH on there. Now, what ranks higher? Okay, this is where it comes into the idea that the prop tells us how many carbons are in the chain. The En is what I call the infix. It's telling us we have a double bond, but we also have a functional group greater than an alkane, an alkene, or an alkyne. So we must include it, and it changes the name. So it's last, it's the highest priority. If it's the highest priority, we have to number from that position. That's why the OH is on the number 1 carbon. Okay, so we have to build this together. So we have 1 right here. So we have alcohol. Okay, we have, this is our 2 carbon and this is our 3 carbon. That's where our alkene begins on the 2 carbon. We have a total of 3 carbons. So we have prop for the 3 carbons. We have 2 and ene because the double bond begins on the 2 carbon. And then we have 1-all. So these are what we call ene-alls. Okay, so the ene is all about the carbons. The all is all about the OH. But because you have to include the kinds of carbons you have and the functional group, we're going to say there's 3 carbons prop. Ene is there's a double bond, and all is a functional group to change the name. So that means when we go to something like this, right here, we have to number 1, 2, 3, 4, 5, 6, 7. Okay, this is not 7 because both of the carbons have to be in the main chain. Both of the double bonded carbons have to be in the main chain. okay? And because all is at the end of the name, it's highest priority, which means we have to number it from there, okay? So this is going to be a to all, okay? So we have 1, 2, 3, 4, 5, 6, 7. So that's heptene, and the double bond starts on carbon 6, 6-heptene to all. And then we have a methyl group here. So we have to start with 6, 6 dash methyl dash 6 dash heptene. This 6 is telling us that it's the alkene is on the 6. This 2 is telling us the alcohol's on the 2. Okay. Now, when in doubt, whatever changes your name has to be the lowest number. So in this case, the alcohol changes the name. It's at the end of the name. Always try to have that at your lowest number. Okay, so let's see. 6-methyl 6-heptenol. Yes. All right, questions on that? All right. Okay, plenty of time. All right. So now, what if you have more than one alkene? Okay, that means we can do diene, triene, and tetraene. If we have more than one alkene, we can name that, okay? So in the case of having, let's say we had this compound here, right here. So we have 3 alkenes, okay? And their longest chain is 1, 2, 3, 4, 5, 6 carbons, okay? So that's going to be hexene, but we have more than one ene. So we have 1, 2, 3 alkenes. So it's going to be hexatriene. Hexatriene. But we have to identify where they are. This is going to be a 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, 6 carbon. So this is going to be 1 comma, because this double bond starts on a 1. We're going to have this double bond start on a 3. So that's going to be 3. And we have this double bond start on a 5. So that means we're going to have 5. So we're going to have 1 comma 3 comma 5 dash hexatriene. And you can do that with as many enes as you have, okay? But cyclic alkenes, we're going to have its own rule, okay? Now, in cycloalkenes, you must label the first 2 carbons in the alkene as your 1 and 2 positions, okay? So it doesn't matter which way you go around the ring, you have to number it so that the 1 and 2 are the alkene, okay? So let's look at that. In this case here, we have, let's do that. We have carbon right here and a carbon right here. Both of those carbons have to be in our system, okay? So now we have cyclopentene. We have 5 carbons, we have an alkene, we have a ring. So we have cyclopentene. So this is right here. Now, if we number from this side 1 and 2, we have a choice. We can say that can be 1 and 2, or we can say it's 1 and 2. Now, we choose the blue numbering, the second numbering system here, because that puts the substituent on the lowest number, okay? So that gives us 1-methyl cyclopentene, okay? What if we had it a little different? What if we changed it to something else? Let's go with that color. 1, 2, 3, 4, 5, double bond, and put it over here, okay? All right, so in this case here, we could label it as 1, 2, 3, 4, or 1, 2, 3, 4. No matter which way we numbered it, we had those first 2 alkenes, carbons, as our 1 and 2, which puts our substituent at number 4. Okay. So what if we had something else? What if we changed this compound to and put a methyl group here? Ooh, now we have an enol. okay? Which means that this has to be our number 1 position because the all is at the end of the system, right? So that means this is 1, okay? But the carbon of the ene has to be number 2. It has to be the next lowest number, so it has to be 2. Now, what that means is, as we number all the way around, our substituent is now on 6. So this would be cyclo hexene dash 1 all, and it's 1 cyclohexene dash all, and then we have to add our substituent, 6 methyl 1 dash 1 dash cyclohexene dash 1 all. Okay, so follow that rule. The 2 carbons are the 2 double bonded carbons are the ones you have to do first. Okay, so in this next example here, we have to use this is 1 and this is 2, because if we labeled this 1 and this 2, that would put our substituent over here at 7. So we're not going to number it that way. We're going to say that's not the way to number it. And so we're going to number it in this direction to give us our substituent at our lowest number, and both carbons are in our 1 and 2 position. Okay, does that make sense? All right, so that's how you do multiple alkenes and and that's how you do multiple groups on a ring. Okay, questions on that? So now we've done alkanes, which all you care about is the longest chain and putting the substituents at the lowest position. Alkenes, you have to have the alkene at the lowest position. Alcohols, you have to have the alcohol at the lowest position. Okay, so those are very important rules to add to your thing. And if you go to Canvas and look at my nomenclature review that we have there, all of those rules are specifically laid out in the system. Okay, so double check that on Canvas. All right. So let's talk about some common names for alkenes. Because they're used so much in the industry and as far as other things to do, they actually have some common names that are a little weird. They're engineering names, but they kind of make sense. They follow a rule. So in the case of this right here, systematically IUPAC, we would say there's 2 carbons and it has a double bond. So 2 carbons is eth. We drop the ane and add ene to make a double bond, so it'd be ethene. Okay, so industrially, they say 2 carbons is the ethyl group, but it still has the alkene. So it's going to be ethylene. Okay, so you'll see that a lot where it's ethylene. There's big tanker cars going around with ethylene or polyethylene, and that's where it comes from. Now, systematically, 3 carbons would be prop, drop the ane, add an ene, and it'd be propene. But because it's a common name, we have it as the substituent plus ene. Okay, so that's important. So you want to pay attention to that as a common name. Now, we also have weird common names for things attached to main chains. Okay, if the compound is like this, we call it the methylene group. Remember, the methyl group is a single bond. That's a methyl group. So a methylene group is going to be a CH2 double bonded to something in the main chain. Okay. But what if you had a group substituent to a main chain here? You have it as both carbons here. It's called the vinyl group. And we can do stuff like vinyl alcohol, which would be C, this thing right here, with an OH, that would be vinyl alcohol. Okay, and if we add 1 more carbon right here, we have what we call the allele group. So methyl is 1 carbon, vinyl is 2 carbons, allele is 3 carbons. Now, why is that important? Well, because we can do, if we have a way to move this hydrogen back and forth, or we have a positive charge, we can have conjugation. So that's why the allele group is different. So methylene group is 1 carbon with a double bond. Vinyl group is 2 carbons with a double bond. Allele group is 3 carbons with a double bond. All right. And those are things to remember. Write that down. Okay. All right. So now let's talk about alkynes. Okay, what are alkynes? Okay, that's anything with a triple bond between two carbons. What that means is that you have a sp hybridized carbon. It has two unhybridized p orbitals, and those two unhybridized p orbitals are overlapping with a carbon next to it. Okay, now there you can have an sp hybridized carbon, for example, in CO2. Notice this is not an alkyne because we have one double bond on one side and one double bond on the other side. They both have to be between the same two carbons. So that's the difference. You must have a triple bond. Okay, so in the case of alkynes, we're going to drop the ane from an alkane or the ene from an alkene and add yne, ine, okay? Now, just like in double bonds, the triple bond has to be in your longest continuous chain, both carbons. And if you have more than one, it would be a diine, triine, tetraine, etc. Okay, so it follows the same rules as the alkene. So let's look at a couple of these and look at this right here. So when we're identifying this, both of these carbons have to be in the main chain. And we want to have the first carbon be at the lowest number. So if we number from this side 1, 2, 3, that would give us a carbon at 3. And if we number from this side 1, 2, 3, 4, that would give us our lowest carbon as 4. Okay, which means we can't number from that side. And we can't number from this because this chain is longer. Okay, so that means we can't number from this side at all because it gives us a higher number and it doesn't include the longest chain. So that being said, we're going to number from this side here, and we're going to number it 1, 2, 3. This could also be 1. It doesn't matter because it's going to give us the same 4, 5, 6, 7. It'll give us the same parent chain of heptyne, heptyne. So it's heptyne, because we have 7 carbons, and it's a YNE because we have 2 double bonds. Now, we have to identify where that is. So that's going to be 3 heptyne. Okay. And we have 2 substituents. We have a methyl group here and a methyl group here. So we have 2, 5 dash di, oops, no capitals. Die, not die. I don't want it to die. I want it to be 2. Dimethyl dash 3 heptyne. Does that make sense? So it's following the same rules we had for alkenes. And what all we have to do is we have to have the YNE signifying we have a triple bond between 2 carbons in our longest chain. All right, so a couple other examples here would be, okay, so now we have 2 carbons here, and we have 6 carbons here. So which one's longer? The cyclohexane is bigger, so it is the main chain, okay? But now we have to prove to ourselves that we have a substituent on there. So we technically have 1 ethynyl. Ethynyl. Ooh, that's hard to say, isn't it? Ethynyl. So if our alkyne is a substituent, we still have to use the YL. YL means substituent, right? So, but we have to show that it has a triple bond. So F says we have 2 carbons. YN says we have a triple bond. YL says it's a substituent. And our parent chain is the cyclohexane. And again, we only have 1 substituent, so it's on the number 1 position. Okay, so what if we have 2 alkynes in the same ring? We do the same rule, diine. Okay, so in this case, we have 1, 2, 3, 4, 5, 6 carbons, but we can't number it that way. We have to number 1, 2, 3, 4, because that gives our alkynes our lowest number, They're at the end. Whenever you're in doubt, whatever's at the end is where you put your lowest number. So we have a 1 and a 3. So it's 1, comma, 3 dash. Hexadiene. Hexadiene. Okay, hexadiene. Okay. Now, if we move over to here, alkynes take precedent over alkenes, which means that our alkyne is at the end, our alkene would be next to it, and our alkane would be lowest priority. Okay, so when we're numbering that, we're going to number from this side first. This is our 1 position because the alkyne is higher order than alkene, which is higher order than alkane. Okay, just like when we had an alcohol, it would be enol. In the case of an alkyne and an alkene, we're going to have ene. Ine is higher priority. So in this case here, we have 1, 2, 3, 4, 5, 6, and then we have a substituent methyl group here. So we're going to say that our hexine starts on the number 1, our hexene starts on the number 4. Okay, so we have -4 hexene -1 -ine, and then our substituent here. So we have our 5-methyl -4 hexene -1 -ine. Okay, does that make sense? Okay, again, the thing at the end has the lowest number possible. All right, so let's do 2 more, well, 3 more. And we're going to see the same thing here. Oh, that's the same one. Let's do this one here. Okay, now, when we have alkenes, we have a choice of cis or trans, okay? So if we draw a line on our alkene and the substituents are on the opposite sides of that line, we call it the trans isomer. Trans meaning opposite. Okay, so if we draw this line and our substituents are on the same side, we call that our cis, meaning same. Okay, so whenever we just have 2 substituents in an alkene, we only have to do cis or trans to say that they're both on the same side of that double bond or they're both on opposite sides of that double bond. Now, if we have more than 2 substituents, we have a different nomenclature for that. And we're going to get into that in a separate chapter. But for right now, we can identify each isomer based on this. Okay, so let's identify this. All right, so which way do we number, from the left or from the right? Okay, well, let's see, the alkyne is going to be at the end, so we have to give that the lowest number. So we have to number from this side. So it's 1, 2, 3, 4, 5. Okay. And because this group and this group are on opposite sides of this double bond, here, so one's on one side, one's on the other side, that means it's trans. So if we build our whole name up, we're going to have trans -2. That's not right. This has to be 5 heptene 2-ine. So it's backwards because we have to label from the ine first. So it's going to be 2,5-heptine. Okay, and that one's backwards also. All right, but that's the cis isomer right here. And it should be 5-heptene 2-ine because 2 should be at the end of the name because it is the highest priority, and the 5 should be here. All right, so I'm glad we found that error in my notes. I need to fix that. All right. Okay, so now we've done alkanes, alkenes, alkynes, and alcohols. So what's the next functional group we're going to look at? We're going to look at halides, alkyl halides, or the halo group. All right, so in the case of halo groups, they do not change the name. They're always a substituent, okay? Which means you're always going to have it on the substituent. And what you're going to do is you're going to follow all the rules. Number 1, you want the longest possible chain. And number 2, because it's a substituent, you still want the lowest number possible. So we would not want to number from this side because we get 3, 1, 2, 3, 4, 5, 6. We'd have 3, 6. Numbering from this direction, we have 2, 5. So we're numbering the chloro first only because it's the substituent we see first, not because it's not changing the name. It's just a substituent. So we're going to do the longest parent chain. In this case, it's 7, so that's heptane. There's no double bonds. There's no triple bonds. It's not an ene. It's not an ine. There's no alcohol. It's not an al. So it's just an alkane. Okay, so it's heptane. And we have 2 substituents right here, making our lowest substituents on the 2 position and the 5 position. Okay, now we alphabetize. Chloro comes before methyl in the alphabet. So we're going to do 2-chloro-5-methyl heptane because there's no alkenes, no alkynes, and no alcohols. Okay, so halides are always substituents. Ethers, the alkoxy group is always a substituent. Okay. So there are some common names for alkyl halides, and it's basically what we would do before, where we take the alkyl group with the YL and add the halogen name behind it. But instead of being iodine, it's iodide. It's IDE, showing that you have a sigma bond between the alkyl group and the halogen. So let's look at this. So if we had this group right here, that would be isopropyl bromide. Notice there's a space here. Common names typically have spaces. Systematic names don't have spaces. They have commas, they have dashes, and they run together. Common names have spaces. Okay, so in this case here, we have the T-butyl group or the tert-butyl group with an iodine. So it's going to be tert-butyl space iodide. So it takes the name iodine to iodide, showing you have a sigma bond between that alkyl group and the halogen. So in this case here, we have a 2 carbons, which would be the ethane, but it's a substituent, so it's ethyl. And we have a chlorine on there, and we have to change that to ide, so it's ethyl chloride. Okay, so it's the alkyl group, space, whichever halogen you have, but you change the INE to IDE. So you can have methyl iodide, ethyl iodide, T-butyl iodide, sec-butyl iodide. So it's going to be the alkyl group plus iodide, or plus the halide, IDE. Questions on that? Okay, we're running up here on 11 o'clock. What I'm going to do is I'm going to do a couple more slides, and then we're going to take a break. Okay, just a 5-minute break, bio break. So we have some common alkyl halides we use a lot. Okay, so these are things you kind of have to remember because their systematic names are a little weird. The IUPAC name for this would be dichloromethane. Okay, because there's 2 chlorines on the same methyl group, but it's called methylene chloride. You're thinking, oh, it has an ENE. Shouldn't it have a double bond? Yeah, that's why it's not a systematic name. Methylene chloride. Okay. If you have 3 on there, it changes the name again. It changes to chloroform. Chloroform. And that's an unusual name, but it is a common name you'll see. It's a cleaning fluid and stuff like that. And actually, methylene chloride is used extensively as a thing that removes paint. It removes paint very well. Now, tetrachloromethane is, the common name is called carbon tetrachloro. So it's saying that you have carbon with 4 chlorines on it, on there. So these are common names, and you should know these because these are very common solvents we'll be using this semester and next semester. So make sure you put these into memory. Methylene chloride is CH2Cl2. Chloroform is CHCl3. And carbon tetrachloride is carbon Cl4. Okay, so these are solvents we're going to use. Other cool ones are this one right here. Remember that the CH2 with a double, yeah, C2H with a double bond is called the vinyl group. Well, let's hook a chlorine on that and you get the same thing, vinyl chloride. And it's very important because this is what we can use to make these polymers called polyvinyl chloride, or PVC. It's a very common polymer that's used in piping and hoses. But the common name is vinyl, for the C2H3 chloride. Okay. Now another one we have is this one right here called tetrafluoroethylene. And you might know the name Teflon, which is polytetrafluoroethylene. So it's basically a whole bunch of them mixed together, thousands and thousands of these together. The trade name is Teflon. The common name is PTFE, polytetrafluoroethylene. All right, the last one you want to know is Freon 11. Freon 11 is used in our refrigerators and our air conditioners, and we use it because it has a very high amount of heat that it can pull away from a system. And the way it's done here is you have 1-1. So you have one carbon, you have one fluorine, and you have 3 chlorines on it. So it's carbon fluorotrichloride, or Freon 1-1, meaning there's one fluorine on the first carbon. All right, so it's at 11. We're going to take a 5-minute break and go ahead and go to the bathroom, stretch, get up out of your chairs. Then we're going to come back and look at conformations of cycloalkanes. I'm going to go ahead and mute my side here and turn off my camera. All right, coming on back here, we're about 11:05 here. We're going to go ahead and continue on. Note that in the chat room, I just added nomenclature activity number 2, which is today's assignment, to our system. And so what we're going to do is we're going to go ahead and break that out right now and take a look at it, and I'll give you some instructions, and then you can finish that. So if you didn't get the email, it should also be on Canvas. Let me go ahead and stop sharing that screen, start sharing this screen. Canvas, share. So again, if we go to our home page here, if we should have both the files and resources and everything here, but if we go to assignments, it should be up here. Nomenclature activity 2 was just added. Thank you very much. I forgot to add it. But here, if we go to files, we can see that we have going down on this under nomenclature activity is the other one. That's the one we did before. There is a second one under activities that is nomenclature activity as well, which you shouldn't see all these files, but you should see the one says group activity 1 nomenclature. So I'm going to go ahead and pull that up. So what I want you to do is, using your notes and using all the rules we just talked about, I want you to go ahead and name all of these things. We're going to continue on with some of these functional groups as we go through here. The name for a group like this is a ketone, and we're going to see that later. And actually, we're not going to do that today, are we? We're not going to do those today. Okay, so don't do the last 3 here. We'll get to those when we do those functional groups. But I would like you to do these, the first 2 on this one, and you can't do those 2 yet either. So do the first few on this one because it has bicyclose and cyclose on it, and do the ones that we've already covered, these amino hexones and the diene. Oh, actually, you can do this one right here. No, it has a non in it, which means it has a ketone in it. So, oh no, that's 9. You can do this one right here as well. So don't do the one that says amino, and don't do the 3 with the carbonyls here. Oh, you can't see my screen? I should have shared this. Am I not sharing? Oh, let's see. I'm not muted, and I'm sharing my video. And okay, you can see it. Can you see it now, Haley? Okay, well, let me unshare and reshare and see if I can get it to go. Reshare. Okay, we should see a screen here. It's the group activity 1 nomenclature. It's technically our nomenclature activity 2. And all right, you can see it. Great. All right, so do everything you can. Dot these 3 with the ketones, with these carbonyls on them, because we haven't finished that yet. And you can do all of these, but this one right here with the amine. So go ahead and get those uploaded by midnight, and then we will have that as a great way to practice your nomenclature that we just started with and get another grade. Okay, another, what was it called? Lower stress grade there. All right, so now I'm going to go ahead and share my screen for my iPad. I'm going to share that. And we're going to talk about different ways to draw alkanes. Okay, so this one right here says conformations of acyclic alkanes, meaning these are straight chain alkanes. Why do I say acyclic? Okay, because when you put things into a ring, it constrains the conformation. It loses that free rotation around the sigma bond. Remember, sigma bond is just 2 electrons shared between 2 atoms, meaning that the other atoms attached to those carbons can rotate back and forth and rotate around. So we're looking for different ways to draw these same things. And we need to remember that these sigma bonds have rotation. double bonds don't have rotation. Single bonds have rotation, double bonds don't. So let's look at our conformation here. And so in this case here, we're having an atom that we're just denoting as the red atom. And we can see that that can be up here, or we can rotate it 180 degrees to be down here. Okay. The only thing that is inhibiting it from moving is the electron-electron repulsion with neighboring atoms. So let's talk about that. So if we have it such that we have an atom here, another atom here, a third atom and a fourth atom all together, we call that a dihedral angle. So let's look at it again over here. So if we look at the angle between this atom here with these atoms and this atom here, the difference, those two atoms that are sticking up from those carbons, that's what we call a dihedral angle. Okay. Now, the reason we want to pay attention to that is that when our dihedral angle is 0, the electron or electron repulsion between those two atoms is pushing them out a little bit. Okay. So that means that there is a energy required to keep them in that configuration. Okay. Now, if you were to take this configuration where your two atoms are lined up on each other like this, we call that the eclipsed formation. So it's like the moon in front of the sun, or the sun in front of the moon, right? Sun behind the moon. So we're looking at this is the eclipsed version, because two of the atoms are overlapping each other and can see each other quite well. Now, if we rotate this 60 degrees, that's the best configuration we can have. We call that the staggered configuration. So in the case where all the atoms are exactly the same size, that means they're going to be as far apart from each other as possible, and this is going to have the lowest energy. Lowest energy because they're as far apart as possible. This one right here, these two atoms are butting up against each other and see each other through space, that electron-electron repulsion. So there's energy associated with that. Okay, so we see what a dihedral angle is, and that there's a difference between the eclipsed formation and the staggered formation. Okay, so let's talk about that. So what's the difference really? Well, it's only 60 degrees. You rotate something 60 degrees, you go from the staggered configuration to the eclipsed configuration. Then guess what? If you do 60 more degrees in that same direction, you're again at the staggered configuration again. So if we can keep rotating this around and around and around. And the only barrier to this is when one atom is next to the other. It prefers to be 60 degrees over here, so they're as far apart as possible from all the other atoms. Okay, so eclipsed is overlapping, staggered is as far apart from each other as possible. And you can just rotate and rotate and rotate and rotate and rotate. There's nothing to stop that except for that barrier to rotation. So let's talk about that barrier to rotation. Okay, so it's hard to see when you draw it out in certain perspectives, but if you have the models, you can see that they're getting close together and far apart. But that's hard to draw. So what we're going to do is we're going to use something called the Newman projection. The Newman projection helps us understand eclipsed versus staggered, and helps us decide which configuration is the lowest in energy and which configuration is the highest in energy. Okay, so what we do here is we're going to do a different representation where instead of drawing all the spheres and balls like this, we're going to look down the axis of the two carbon atoms. Any two carbon atoms, you can draw a Newman projection. Okay, now the reason we're going to do this here is we're going to draw a line here, because then that means we have 1, 2, 3 spheres that are closest to our perspective. And then we have 1, 2, 3 spheres, atoms, further away from us, okay? So paying attention to which ones are closer and which ones are further away is how we account for our Newman projection. And the way we do that is we put the atoms closest to us together on a pinwheel, like this. And then this represents the atom behind let me draw it a different color. This represents the atom behind and the three things attached to the atom behind. Okay, so the one where they meet in the middle are the closest ones to us. The ones where they meet on the ring are the furthest away from us. And so that's how we can get our perspective there. So that means that these hydrogens here, 1, 2, and 3, are closer to us, sticking out at us. And these hydrogens here, 1, 2, 3, are further away and sticking away from us on that second carbon. Okay, do we see this representation? Okay, so when we draw our Newman representation, instead of having to draw our spheres rotating and overlapping, what we can see is when we go our 60 degrees from our staggered configuration to our eclipse configuration, we see that the hydrogens on this case are overlapping each other. In fact, all 3 front hydrogens are overlapping all 3 back hydrogens. Okay, so write that down. All 3 front hydrogens are overlapping all 3 back hydrogens in the eclipsed formation. And then all we have to do is turn it another 60 degrees and we'll get back to a staggered configuration. Okay. So this has the same energy this has because they are the same distance apart from each other. Okay. So if we take that and we want to learn how to draw our Newman projection, the best way to do it is to pick a carbon. So what we're going to say is you're going to pick carbon 1 and 2. Sometimes I'll say pick carbon 2 and 3. And so, for example, if you had a butane, I'm going to say you can choose carbon 1 and 2, which is going to give you 1 Newman projection. Or I want to say you want to draw down this axis here. And so I'm going to say put your eye here, and we're going to draw it on 2 and 3. So we have to pick 2 carbons. That's what we have to do first. Okay, so let's pick 2 carbons. And then the next thing we have to do is we have to figure out which carbon we're going to look at first. Which carbon's going to be in the front? So in this case here, I like to draw a little eye. I do like this little thing that looks like an eye, and I'm looking at this direction here, okay? Which means this is our carbon that's in front, closest to us. And this is our carbon that is behind that. Okay, and the way we draw that is we start with the carbon in front is the dot. And we draw the 3 things attached to that. Then we draw a circle representing the carbon number 2, the one behind it. And we draw the 3 things associated with that. And therefore we get our Newman projection. Okay, so what you have to do is, number 1, find out which 2 carbons you're going to look down. Okay, you're going to line those carbons up. You're going to put a dot for the carbon closest to you, a ring for the carbon behind it, and then you're going to attach all the substituents to there in that same perspective. Now notice, in the case of this right here, we have this hydrogen is on a wedge, so it's facing out at us. This hydrogen, this carbon, and this hydrogen right here are all in the plane of the paper. Okay. And this hydrogen and this hydrogen are on dashed wedges, so they are going to be pointing back from us. So that means if we're looking down this perspective, let's take away all that stuff. If we're looking down this perspective, that means this hydrogen is going to be on our right in the lower side, because that's where it is on that carbon. So that's going to be this hydrogen. Okay, now this hydrogen is going to be straight up because we're looking at down that carbon-carbon line. It's the one above those 2 carbons. So that makes it this hydrogen. Okay, and the last one here is the one going back. So it's going to be down and to the left. So that's going to be this hydrogen here. Okay, so those are the front 3 hydrogens. We do the exact same thing for the back 3 hydrogens. We're going to say this hydrogen is in the plane of the thing. It's going to be pointing straight down. It's not coming out of the plane of the paper. It's not going into the plane of the paper. So it's going to go straight down. So that makes it this hydrogen. We have this one right here. It's coming out of the plane of the paper. So it's going to be up and to the right. So that makes it this hydrogen here. And our last hydrogen is the one that is right here. It's up and to the left. So that would be this hydrogen here. Okay, so that's how we draw our Newman projection. So let's look at our front carbon here. Again, up and to the right, up and to the left, and down straight in the middle. Up and to the back, left and to the back, right and to the back. Does that make sense? Okay, so the easiest way to draw this is to do it in a system. Okay, so you're going to pick, let's call this a CH3 group, call this a CH3 group, and we're going to assume everything else is hydrogen. I'm going to say you must do your perspective from this thing. So it has to be this carbon and this carbon. Okay, so that means we start with a line in the middle, and notice this is in the plane of the paper right here, and we're looking at it from this side. Okay, which means our CH3 group is going to be sticking up in the same plane as these two carbons, and it's in the same plane as this CH3, which means that when we draw our back carbon, our CH3 is going to be down here. Okay, now we have to fill in everything else. We have to show where all the hydrogens are. And so we have coming out in front of us, we have the other two hydrogens here, and we have the other two hydrogens on the back carbon. Okay, so I like to start from the front, get that perspective done, and then fill in the different system. Okay, so if we were to draw this one right here, this is our front carbon. So we're going to draw a line here. We have one hydrogen here and one hydrogen here. So it's going to be in those two directions, and then one hydrogen here, there. Then we're going to switch to the back carbon right here, and we have one up and two, one to the left, one to the right. So we're going to draw a ring, one up, one to the left, one to the right. Okay, does that make sense? All right, now, why is this so important? Well, now we can see where our groups are and whether or not they're rotating one direction or the other, and we can see whether they're eclipsed or they are staggered. Okay, so let's look at this. When we have our drawing here now, when we have all of our substituents as far apart as possible, they are staggered. And staggered is more stable because, remember, the outside of those hydrogens are electrons, and electrons repulse other electrons, so they want to be as far apart as possible. The only thing holding them together is that bond, that sigma bond, right? So when we're staggered, we're at the lowest energy conformation, the most stable energy conformation. Now, all we have to do is rotate 60 degrees and we get to our eclipse conformation. This is less stable because those hydrogens are now seeing each other through space and they're trying to push each other apart. But not only do we have one hydrogen-hydrogen reaction, we have two hydrogen-hydrogen reaction, three hydrogen-hydrogen reactions. So when you go from your eclipsed, in your eclipsed stage, you actually have three different electron or electron repulsions, making it less stable. Okay. All right. So what does that look like? Let's graph the rotation of those hydrogens as a function of energy. Okay. So if we start off at 0 degrees, which is where we are eclipsed, the hydrogens are eclipsing each other, right? We have a higher energy, less stable. We have a higher energy, less stable state because we have that electron-electron repulsion. And it equates to about 3 kcals per mole, okay? Which means there's 1 kcal per mole energy required for each of those hydrogens. That's the energy barrier, okay? Now, let's go 60 degrees, and we're now in our staggered configuration. This is our lowest energy. So the difference between 60 degrees and 0 degrees is about 3 kcals per mole, or about 1 kcal per hydrogen, okay? Now, again, that's not very much. I mean, that's a little bit of heat, right? And so it can go 60 degrees and get to that higher state, 60 more degrees, lower state, 60 more degrees, higher state, 60 more degrees, lower state, and then we get back to here. Why do I keep going around? Well, we're looking at these two hydrogens and watching them walk all the way around until they're back to that staggered state. So from 0 degrees to 360 degrees, this hydrogen is going all the way around, okay? So if it's going all the way around, that means it has 3 different places where they're staggered and 3 different places where they are eclipsed, okay? And so this is the same as this, okay? So that's just with hydrogen, okay? What if your group's bigger? You're gonna change the energy. All right, so let's look at a Newman projection of something more complex than just ethane. Let's put a CH3 group on there, okay? So when we do that, we wanna look at where we want to draw our line. So in this case here, we're gonna draw our perspective down these first 2 hydrogens, okay? Which means the methyl group is gonna be on the back carbon, okay? So if we do that, we're gonna wanna draw our front carbon with our 3 hydrogens here. And then we're going to draw our back carbon, and the methyl group is going to be on the back carbon. So we're going to draw it down here. And it's always best to draw in the staggered configuration because it's easier. Okay, now, once we have it in our staggered configuration, let's go ahead and redraw it in an eclipse configuration. The only thing we have to do there is to rotate these by 60 degrees. So we're going to do that same thing. And you should end up with a structure that looks like this. You have your 3 hydrogens here. Draw your back carbon. You're going to draw your CH3 group here, your hydrogen here, and your hydrogen there. So front carbon first, second carbon second, and then make sure you have all your substituents. Okay. So now that we see this, the CH3 group is even bigger than a hydrogen group. So is that going to be more potential energy or less potential energy? You're nodding more, I can tell, even though none of your cameras are on. Anyway, I can see it. Okay. Anyway, so let's go ahead and extend that 1 more carbon. Oop, not that. Let's extend that 1 more carbon and look at butane. Now, we can do butane in 2 different ways. It depends on which 2 carbons you want to look down. Okay, so in this case here, we're going to do butane, but we're going to look down 1 and 2 first. What that means is the 1 carbon is going to have 3 hydrogens on it. The 2 carbon is going to have 2 hydrogens and an ethyl group. So our 1 carbon is the one in front with 3 hydrogens on it. Boom, boom, boom. And our back carbon, our second carbon, is the one with 2 hydrogens and a CH2 group. That's different than if I told you to draw it between the 2 and the 3. If I told you to draw it between the 2 and the 3, that means that we would want to, trying to get to red here, I want the perspective down here on this bond here, which means we're going to have a methyl group on the front and we're going to have a methyl group on the back. So it's going to be different. So we would draw our 3 bonds that goes to our front carbon. We're going to put 1 CH3 here, 1 hydrogen, because we're drawing this number 2 carbon. And then we're going to draw our back carbon with a CH3 on it and a hydrogen and a hydrogen. See how the different Newman projections come from which 2 carbons you're looking down. Okay, so that's the important part. You need to know which 2 carbons you're looking down. Okay, so in the case here, we're looking down the 2-3 bond. In this case here, we're looking down the 1-2 bond. Okay, now, what if we look down the 3-4 bond? Well, it would just reverse things because we would have the ethyl group on the front because the 3 carbon would be in the front, and then all the hydrogens would be on the back. Okay, so you can draw your perspective any way and it will be accurate. Just make sure you're using the correct 2 carbons. Okay, so now if we have only hydrogens, you only have 2 possible configurations. The 2 possible configurations are staggered and, what's the other one? Staggered and eclipsed, right? Okay, but now that we have one group that's bigger than the other, we now have 2 possible other systems. Now, in the case of having the 2 largest groups 180 degrees apart from each other, we call that the anti-configuration. So if we looked at our butane again with our CH3 up here and our CH3 down here and our hydrogen here, and hydrogen here, hydrogen here. So our two biggest groups are 180 degrees apart from each other. That is the anti-configuration, okay? So that's the best case scenario. The biggest groups are as far apart from each other as possible, and they're in that staggered conformation. So they're really, really happy. That's the lowest energy state, okay? But what if we rotated this 60 degrees, okay? So all I'm gonna do is rotate this 60 degrees, and we're gonna do, let's see, a hydrogen, I'm sorry, not 60 degrees, 120 degrees. So I'm going to rotate this to this position, this to this position, and this to this position, keeping the methyl group down here, keeping the back group not rotating. And I'm going to put the CH3 here and the hydrogen here. So all I've done is rotate this group to this position. Okay. In this position, our two largest groups are now not staggered because they're still in a conformation. They are gauche now. Gauche means that they are close together, but they are not eclipsed. Close but not eclipsed is the gauche configuration. Opposite each other, anti, close but not eclipsed, gauche, eclipsed is eclipsed. Okay, and that's even higher in energy. So anti-configuration is the lowest possible energy. The gauche is slightly higher in energy. Okay. All right, we got 10 minutes to power through. Just keep with me. Okay, we got 14 down. We dropped somebody. I don't know who we dropped, but let's talk about that. All right. So in our anti-position, that's going to be our lowest energy conformation. By rotating 60 degrees, we're now going to be eclipsed. But in the first eclipse, we have a hydrogen butting up against a methyl group and a hydrogen butting up against a methyl group and two hydrogens butting up here. So that's not too bad. I mean, it's worse than hydrogens, but it's still not too bad. Rotate it 60 degrees, we now have our two methyl groups close to each other. So this is staggered, but it's gauche. Those two largest groups are 60 degrees apart. Okay, so that must be higher in energy than anti. So staggered anti should be the lowest energy conformation. Anytime it's eclipsed, it's higher than any other staggered configuration. Okay, so let's rotate this 60 degrees. Oh, now we're eclipsed, but now our two biggest groups are closest together, right? So that means they have to have a higher energy level. But hey, we still have rotation, so we can get these back to a gauche, back to staggered. Notice it's the opposite of this one. It's just on the other side because all we're doing is we're rotating the back carbon around and around. And then we get to an eclipse configuration, and then that gets us back to our staggered anti-configuration. So what does the energy diagram look for that? Well, it looks a little different because we have what we call steric strain. The methyl groups are bigger than hydrogens because they have three other hydrogens associated with it. They still have that electron-electron repulsion. So that means they're going to stretch that bond out and give this strain to the system. And then we call that steric strain. Steric meaning that they're close to each other, meaning electron or electron repulsion. So they want to get, so that means our hydrogens put less steric strain on it than a methyl group was because a methyl group is bigger. Okay, so if we look at the different energy levels of that, we can see that we have a different, configuration now. Okay, so in this different configuration, instead of going from staggered to eclipse with just hydrogens, we only saw one energy was high, one energy was low. Now we're going to have more interactions here. So the first interaction we have is our lowest energy interaction, anti. They're as far apart from each other as possible. Then we have our first eclipse where we have a carbon, a methyl group hydrogen, a methyl group hydrogen, and a hydrogen-hydrogen interaction. So that's okay, that's not bad, but it's still higher in energy. But when we go to this Gauss configuration, we have a higher energy than if they were anti. So it doesn't go back down to zero like it did before. It's still higher. Then when we have our two methyl groups interacting with our two hydrogens here and our two hydrogen here, that's our highest energy interaction. because those two largest groups are eclipsed. Now, if we rotate another 60 degrees, we can get to the other gauche. Notice that's the opposite mirror image of it. And then we go to just a methyl hydrogen, hydrogen eclipsed. And notice these two are also the same in energy because they are mirror images of each other. And then we get back down to the lowest energy one, the anti. Okay, so that means that anytime we see these systems, this rotation around this bond, we want to look for the lowest energy one, knowing it's anti. But we also have two other semi-low in things, which will be our gauche. Our gauche is going to be the next lowest energy. Eclipsed is always higher in energy. All right, so what about multiple attachments? All we have to do is worry about our perspective, okay? So what we're going to do is, let's start with this, and we're going to go down this bond right here. We're going to look down. Oh, that's a horrible looking eye. We're going to look down this bond here with our eye over here. And that means we're going to have one methyl group on the front, one methyl group on the front, and a hydrogen on the front. And then we're going to have on the back carbon, we're going to have one methyl group and two hydrogens. Okay, so looking down that perspective, when we first draw, we want to draw the stuff in front of us first. So we have a methyl group, and a hydrogen on the thing in front, a hydrogen, and a methyl group on the thing on back. Okay, so because we have two methyl groups, we can never be 100% anti. Okay, we're always going to have one of them in the gauche position and one of them in the anti position. Okay, but that doesn't mean there's not a higher level configuration. Here we have these two in the anti and these two in the gauche. Okay, that's lower in energy than having all three of them in gauche. All three of them in gauche is higher in energy. Okay, so you have to look at it from perspective. Now in this one right here, we're again doing the same thing. We're going to draw that perspective line from this angle here. So we have two methyl groups on the front, but then we have two methyl groups plus a T-butyl group. So we have methyl, and T-butyl behind us. And now we're going to see that we can have very, very high number of interactions. The methyl groups are almost always going to be gauche. The T-butyl group is almost always going to be gauche or something. And there are a lot of more energy barriers to getting this thing to rotate. Okay. And I'm going to stop there, and we're going to continue on to zigzag configuration and chirality tomorrow. Okay. So go ahead and don't forget to do your nomenclature activity. Use the rules we talked through today. Only worry about alkyl halides, alcohols, alkenes, alkynes, and alkanes, and bicyclo compounds. Upload those, and hopefully I'll be feeling a little better tomorrow, and we can continue on with chapter 4 and finish up chapter 5 on as well. All right, questions and or concerns? All right, I will go ahead and stop recording.